I'm Jonah. I'm the build lead for our team, and then some of the other presenters are our build team, so they can introduce themselves while we're waiting for this to pop up.
Chris. I am actually not on the build team. I'm the team lead person.
I'm Thomas. I'm on the build team.
I'm Evan. I'm also on the build team.
Okay, so hopefully everyone can see this, but this is our design and build presentation. So in this, we'll give you some tips and tricks on all the different kinds of mechanisms and ways to build those mechanisms that you'll need to do this season. And this is all taken from our personal experience.
So first thing we want to talk about is the FTC design process, or design process in general. So this is, relevant to mechanisms, how to get from your problem, which is defined in the game manual, to your solution, which is your robot. So, zoom to cover this up. All right. This is kind of the outline of the design process that we use. You got to read and understand the game manual. So that happens on kickoff day. You watch the video and you read through the game manual, look at all the specific rules and stuff. You brainstorm with your team. You research into what has been done before in FTC, what other teams are thinking of, physics concepts you need to look up, or any sort of industrial machines or robots that you think could be kind of similar to how you would want to build your robot, or ideas you want to kind of borrow from the industry. Prototyping multiple solutions to your problem, testing those prototypes, selecting which one of those prototypes is best to design that final mechanism in CAD or something like that, test that mechanism, and iterate as needed. So the first steps are reading the game manual and discussing it with your team. So usually after kickoff, we've watched the video and we come back to our room and we will pull up the game manual and look through all the relevant stuff to make sure we all understand how exactly to play the game, because you'll see the video on kickoff, but it'll be a bit vague and there will be some stuff that's kind of poorly defined. So you really want to read through the game manual and figure out exactly how to play the game legally, what scores points, and come up with a strategy. So after that, you do an open brainstorming session. So you ask for ideas on how to solve the problem. Let's say if you got to pick balls out of a crater, how do you solve that problem? Get everyone's ideas, no matter how crazy, write them down, maybe on post notes, maybe on a whiteboard. Spend a good while getting a lot of ideas out there. Then figure out what ideas could be kind of combined. If you have two similar ideas, can you combine them into one? Are there some that are just not feasible? Is someone wanting to do a vacuum to vacuum up balls? That's probably not feasible in FTC, probably something you shouldn't prototype. And then just narrow it down to select a few options per mechanism to prototype. We usually give 1 or 2 people each mechanism. And so if you're working on a mechanism, look on YouTube and FTC forums to see what others have done in the past for inspiration. Like I said, look for industrial examples. There's tons of machines out there that may have to manipulate similar objects that you have to, or similar shapes in a similar way. If you can think of any of those, or if you have parents that work with machines like those, or you can find them on the internet, those are great resources because people who design industrial machines are pretty smart. So next up is prototyping. To prototype, all you have to do is build a proof of concept that should function similarly to the way the final mechanism will. It can be built very not sturdily, and just meant to last for while you are demonstrating it. So if you look at the beautiful picture here, that's an example of our collection prototype from Rover Ruckus. That was our game 2 years ago. It is made out of cardboard and other scraps we had lying around. The other good thing about making it this way is you can change it rapidly. So if something didn't work with like our cardboard dimensions, we could change that really quick. Really lets you change rapidly and figure out what works. After all the prototypes are done, you really want to compare all the prototypes and see which one does the best. So for example, which one is the most reliable at picking up the elements in a certain amount of time or something like that. You can define your own criteria, but you do want an objective way to measure them, and you want to write that down and notate it, because that's one of those things that's really good for the Think Award, as well as helping your robot. So next up, you have to design and then build the robot. So if you see, you got to translate the prototype into a reliable and robust mechanism. And if you see there in the center, that is what the prototype you saw before became. The collection thing with the rubber bands and CAD is what you saw in the prototype before. Yes, thank you. So you got your prototype. You don't want to deviate too far from it, because you know that works. You obviously will need to make some changes to make it work on the robot, but you want to keep the same principle and come up with a way to make that well. So you got to make a model of it in CAD, or if you don't have CAD or don't know how to use CAD at this point, dimension drawings can be good. Just make sure it'll fit in with other stuff in your robot and that it will, fit and work. When you're designing it, you really want to make sure to use strong parts and attach them sturdily. You want to have multiple points of contact, and when you build the final assembly, it should be fairly rigid and sturdy to withstand the force of gameplay, because when you actually are out there competing versus practicing, it is a lot more stress on the components. Some things you want to try and shy away from in your final design to help you get that sturdiness is materials that break easily. So like duct tape or stuff like that. Stuff that wears out fast. Example of that can be like rubber bands sometimes can wear out too fast. Stuff that gets loose, so if it's like set screws are usually not good unless you Loctite them, or unless they have some sort of other backup, or things that can change properties over time. So you want the mechanism that you design to be the same the day you design it to the day you compete with it. Yeah. So next up is testing and iterating. This is kind of the final spot of the design process, although it can loop around and you can do some more with it. So not everything is going to transfer perfectly into the final build. You're going to have CAD that may look good or drawings that may look good, but something goes wrong and it just doesn't work quite the way you thought it would. So that's why you want to have all this stuff designed and built a few weeks before the competition to work out these kinks. Some issues may require a slight redesign, so you may need to reprint a 3D printed part. Some may require changes that are between very janky if you're close to a competition, or it's not pretty, but it works pretty well. So as you can see here, one of the things that's not pretty but works really well is this rev bar on this collector. So Razzlemon, if you can point at the collector. Oh, not at the collector, my bad, the deposit mechanism. To the upper, there you go, right around there. There is a bit of silver you can see, and that's a rev bar that we put on there to weight it down. Wasn't in our original design. It's not exactly pretty, but it works really well. Sometimes you may need to significantly redesign a portion of the robot, which is why you really want to have that bit of buffer. I don't mean completely redesign the mechanism. I mean make significant functional changes. Long story short, the more time you give yourself to test, the more reliable your robot will be at the competition. Also, between competitions, you can try and improve and iterate mechanisms, but you really want to make sure that you don't take apart a mechanism or take it off the robot if you don't have something better to replace it, because you don't want to go from a good robot to a worse robot between competitions. You want to improve, obviously.
So next up, we're going to talk about drivetrains. And drivetrains are really the base of your robot. That's exactly what they are. So you want to make sure you have a sturdy one that can accomplish everything you want it to. So there's a bunch of different types of drivetrains, and here are just some of the most common configurations in FTC. So you have the 4-wheel, 6-wheel, Mecanum, X-drive, H-drive, treads, and a swerve drive. And some things you want to consider when making your drivetrain is you want to think about how fast you want it to be, how much power you want it to have, how maneuverable you want your drivetrain to be, how much traction your wheels are going to have, and what type of terrain you have to go over, and if you want it to be omnidirectional, which means it can move in more directions than just forward and backwards. So probably the easiest drivetrain to build is the 4-wheel. And so there's really three main different ways to build a 4-wheel. But at its base, it's just 4 wheels with a motor attached to them. There's nothing complex. But you can change it depending on what wheel you do. So if you use just normal wheels or like 4 traction wheels, you can get pretty good traction, but you're not going to have as great as maneuverability. But if you have 2 traction and 2 omni wheels, which are wheels that have rollers on them that allow you to go forwards and side to side, then you're going to have this off-center rotation and you're going to have pretty good traction while still having good maneuverability as well. Unlike the 4 omni wheels, which you're going to have very, very good maneuverability, but you're not going to have nearly as good traction, so you're going to be able to be pushed around a lot during gameplay.
So the next drivetrain we have is our 6-wheel drivetrain. And this design is actually one we used back in Rover Ruckus. So the pros of it are it's high traction, so it's really easy if you want to push other robots around, and it's really hard for other robots to push to you. It's really quick because you got all your motors driving in the same direction, and you have very little loss, like slipping or anything like that. As well as it can go over like difficult terrain. So it can easily go over, like this past year, it could have easily gone over the center if you needed it to. However, it can't strafe, which is a big downside, because a lot of times in FTC, it's very helpful to be able to adjust side to side without having to like back up and turn. It takes a lot less time if you can strafe. And it's a lot of space that it takes up within your size and constraints of your robot. So as you can see, it takes up our whole side on each side, as well as the motors come into the center. So it's not ideal to have that much space taken up. And then we have our Mecanum, which it's great because it can strafe. It's really high maneuverability because of that. So it can go all over the field. And if you want to, you can even design it to work around terrain. Like look at 7 Sigma and Relic Recovery. Or Rover Ruckus, my bad, not Relic Recovery. And it's really useful in almost every single year of FTC because of the fact that it can strafe and move really quick. However, most designs of Mecanum drives only work on just like flat fields, pretty much. So it's a lot more work to get it to go over terrain and stuff like that. And it's a lot more work to like program it because of the way that the wheels function. You have to like create a drive system that does all the math within your program to drive in a direction rather than just running all your motors in one or another direction on one side.
So next up, we have the X Drive. Some of the good things about this is that it can maneuver very well, and similar to the Mecanum, it can strafe. Some of the things that aren't so great about it is that your motors are going to be facing in towards your robot, and that's not always great because that takes up more space inside, whereas some of the other drivetrains, you can hide them a little bit better. And it takes up a good amount of space. Similar to the Mecanum, it also is pretty complex to program because you're not just going to be going forwards, backwards, and turning. You've got to run the wheels in ways to strafe and stuff like that.
So next up we have the H drive. So this one is also a semi-strafable drivetrain because you have that center wheel. And so some of the pros are it's pretty good maneuverability and that you can strafe, but it's not as fast as strafing. And the cons are, as you can see, it takes up basically the whole bottom of your robot, so you're not going to have much space for other things. And it also uses an extra motor because you're only allowed to have 8 motors. And if 5 of them are on your drivetrain, you're not going to have that much for other mechanisms. And since they're all Omni wheels, it's not going to have the best traction either.
So our next drivetrain is the tread drive, or sometimes called the tank drive. Its pros are it has decent traction, and it can it's better than most drivetrains at going over like difficult terrain that's like built into the field. However, it has really poor maneuverability, and a lot of times it can like slip and stuff. It's prone to breaking because there's so many different connections on your belt, like your drives, and you have to pay more if you want to get better performance out of your treads. So a lot of the cheaper treads will be like plasticky and slip a lot on the field, even though it's made of foam. You really need to look into getting like rubber coated treads if you want to get good traction out of the drivetrain. And then I think our final drivetrain is swerve drive. It's really, if you can pull it off, it's really good. It has great maneuverability. It can go really fast and in any direction. And as well as that, it has great traction. As you can see here, we don't have any rollers on these wheels like we did with some of our other drivetrains that could strafe. But instead, we're actually rotating them, like the wheels themselves, which makes it a lot more complex to do. And so you have to have all 4 of those motors like you normally would on a drivetrain, but you're also committing 4 servos to your drivetrain, which is obviously a lot more of a commitment and a lot more of a space commitment as well. Usually they end up being taller, so you get less space to put all your mechanisms on top of the robot. And yeah, as well as those 4 extra servos it uses.
Hello, I am Allie. I am also on the team. All right, so I saw one question come through. For the drivetrain with 2 Omni and 2 traction wheels, where would the Omni wheels be placed?
Yeah, so typically the Omni wheels are placed on the front of your robot, and both of them are on the front. And then like you have higher traction wheels would be in the back. So then your back, say you want to turn, the back of your robot won't move while the front of your robot will be turning. So that will it's just a different type of rotation. Like if you ever seen a cart that has 2 swivel wheels in the front and then the ones in the back don't move, that means the front of the cart is really easy to turn, but then the back won't turn. It's just like that.
So
Awesome.
Max from 8 to Automate asks, can you explain strafing?
So strafing is basically the ability to move your robot not only side to side, but like in any direction without turning. So basically, if your robot is sitting straight, like pointed at something, and you're slightly not lined up, you can shift sideways to get to a point where you are lined up with that thing. So like what you see here is this center wheel would rotate to shift your robot sideways because of these rollers on all of the Omni wheels. It allows it to roll side to side, but if you combine all of those motion together, you can get diagonal movement as well.
Which drivetrain seems to be the most common based on your experience?
So honestly,
A lot of it depends on what the challenge is, and and what you can do. The most common and the most versatile by far is the Mecanum wheels and the Mecanum drivetrain, because it's got a good balance on maneuverability and traction, but it is a little bit more complicated to do. It does work in most cases, but if you're just starting out, something like a four-wheel might work better. So it really, a lot of it depends on what your challenges are and what your resources are. But in most cases, Mecanum is the more well-rounded and the one that is going to be the best solution.
And I
One
would
thing to
argue,
point out with the Mecanum wheels is they are much more expensive. So if you are on a tight budget, Mecanum wheels are probably not the way to go, because like I think for a full set on Go Builda, it's like $160 for all the wheels, which some teams may not have the budget for.
and that does remind me, do not get, I would not recommend Vex Mecanum wheels. They are cheaper, but they are probably not worth it. But a good set of Mecanum wheels, even though they are expensive, is worth it. Next question. When deciding between two prototypes, even if one performs better than the other, do you keep in mind that there could be significant difference in a performance when mechanisms are turned from a prototype into a final version?
So one of the things you want to think about when you're prototyping and you have one mechanism performing better or worse than others is you want to think about like why they're performing better or worse. If it's because something on your prototype is spaced slightly wrong, I would try to go and fix that and try to make your prototype perform as best as it can to try to get your team the best design that's available. But if it's something where your wheel, like if you have like a wheel intake and it's causing something to like your game element to like flick around and stuff like that, then if it's like an inherent issue with the prototype design, that's something where it's obviously not the correct design. But so it is important to keep in mind that there can be slight performance differences from your prototype to your final, but you got to think about like where those performance differences are coming about. Is it coming about through differences in the build quality, or is it coming around in is it coming around in actual design differences? So if it's the design differences, you want to go with the best design. But if your build quality is what's causing the issues, then you might want to like do a slightly better prototype of it to see if you can get it to perform better.
All right, I think that's it for questions. So we'll be moving on to the next section and doing some more questions soon.
So next we're going to be talking about drive methods. And this is basically how you get your motor to drive whatever it is that you're trying to drive. So you get the motion from your motor and you translate it into whatever you're trying to drive. The four that we're going to be going over are direct drive, chain drive, belt drive, and gear drive. Before we get into some of the different driving methods, I'm going to talk a little bit about gear ratios because they come very in handy, and they're very important when you want to consider how you're going to design your mechanisms and your drivetrain. So basically what a gear ratio is it's when your speed or torque of your system changes because you're changing the diameter of whether what you're driving or what is being driven. So we have an example over here to the right, and there is this example is depicting a very simple pulley system where the red driving pulley is twice the size of the driven pulley, so that creates a 2-to-1 gear ratio. And what this means is that when you spin the red pulley, the blue pulley will spin at twice the rotations per minute, but it will have half of the torque. So that's something that you want to keep in mind. there are a few different places where gear ratios come into play when you're designing your robot, especially for the drivetrain. The first one is with your motor. The actual rotations per minute of the DC motor coming from the DC motor to the shaft that it's driving is changed by the gearbox in the motor. And then from there, your drive method, which we will be talking about in the next few slides, such as using pulleys or gears or what have you, that will also has the potential to add or change your gear ratio. And then the final thing, if you're looking at a drivetrain, is the diameter of your wheels will change what your gear ratio is.
So,
One of the driving methods is chain drive. Chain drive is when you have sprockets from your motor to whatever you're driving. Some of the good things about this is that you can change where your motor is mounted, and you can also change your gear ratio, as was mentioned earlier. A good thing about chain, as opposed to some of the other ones, is that you can change how long your chains are and how far your motor is away from whatever you're driving. In this case, it is a wheel. Some of the worst things about a chain drive is that you have to tension your chain, and each individual link is a point of failure, so that could cause problems with your chain breaking, and it would stop working, require maintenance. Another thing about chains is that they stretch over time because each individual link will wear down slightly, and when you multiply that over a factor of tens of links, it causes problems, and it will actually change the length of your chain.
So the next drive method is direct drive. This is by far the easiest one to do because all you have to do is stick the wheel right on the motor shaft. And so that's one of the pros. It is very simple. But the problem with it is that there's like no flexibility in the motor position, so that you have to put the motor right on the wheel. You can't move it around. And it also wears down the motor gearbox because it's not the best for the wheel to be right on the motor. Plus, you're not able to do any of the gear ratios, so you have to do whatever is the gearbox on the motor. But one of the things that is good about it is there's fewer points of failure. So you don't have like 80 different chain links that could possibly break. You only have the one shaft. Next is the belt drive. So with belts, you have to be incredibly precise when positioning, and if it's over tensioned or under tension just a tiny bit, it will throw your whole drivetrain off. But the pros are, just like chain drives, you have flexible motor positioning, and once you get it up and running, it's incredibly low maintenance. And it also has a very variable gear ratio, and there's much fewer points of failure. Plus, there's less backlash than chain, and it's much lighter than chain. But the cons are that, like I said, it requires very precise positioning. It has to be 100% exact. But companies like Obilda do make belts that fit exactly with their channel. So if you wanted to go into belts, I'd use their website. They have a belt calculator built into it. They also require tension. If say you don't have the right size belt, you need to tension it down. Plus, these belts can be much more expensive than other options. Belt, and especially if you want to buy extras, which we always recommend having at least 2 extras of everything on your robot just in case something goes wrong. Then it costs a pretty penny to do belts.
So next up is our gear drive. One of the big issues that people have a lot with gear drives is that if you start getting slipping or skipping on your gears, then you can start to grind down your teeth, and then your gears become useless. And along with that, each tooth on a gear is another point of failure. So your entire drive method is covered in points of failure. However, the pros are it gives you a pretty flexible motor position. Even if you're using bevel gears, you can even like unlike it's depicted here, you could put the motor inside of that channel that you see there and drive it at a 90-degree angle. The gear wheels at a 90-degree angle. And it also gives you a very variable gear ratio. You can, a lot of times gears will give you a pretty good gear ratio, like difference if you want it. So you can get a very small gear driving to a very big gear, or you can get like medium gears. So just like within your space, there's a lot of different options that you have to change your gear ratios. However, as I said before, it can slip and grind, and then you have to go in and replace the gears. So that's something that if you're going to use gears, you need to make sure you have backups for at least every gear, just in case you have issues at a competition. And so then we have some tips and tricks. One of those is to make sure that you take advantage of the shape of your shafts. So with D and hex shafts, if you're like 3D printing or something like that, you want to make sure you're printing like pretty close to the shape of that shaft, just so that you get the inherent rotation from the shaft without getting a bunch of loss. If you're trying to do like on a circular shaft, it's a lot harder to get something to spin correctly. You also want to use consistent structure pieces, and one of those that's really common is like go build a channel pieces or Tetrix channel pieces. Um, those will give you pretty good structural integrity, as well as a lot of mounting holes that you can use to build off of. And then another thing you want to do is before you get into building your robot, or building any of your big assemblies, you want to try to CAD it. And like, so you have a full design of your robot put together is ideal. That way you know what you're doing before you just go start building things. You also want to plan your drivetrain, which is another part of CADing, is you're planning out every single mechanism that's going on to your drivetrain. You're making sure you give each mechanism enough space to function properly. And if you have mechanisms that like lead into one another, such as a collection going into an output, you want to make sure you have a really good transfer in between those two.
Before we get into questions, there's just one more thing I wanted to add in about the belts. So say if you're designing a piece and you've chosen you wanted like a 48 tooth to a 24 tooth, and you get a belt distance of like, I don't know, 100, but there's like only like a 100 tooth belt, but there's only like a 97 and a 104 tooth belt. Don't buy one of those two belts. Instead, I would recommend changing either the location of your belts or the size of your pulleys to make it so that you have exactly the amount of teeth that you need. So basically, I would recommend, instead of picking your belt around your like drivetrain build, I would build your drivetrain around what size belt you're going to pick.
All right. I do not see any questions in the chat right now. Yeah, we're gonna have another question break in the future. So any questions, just throw them in the chat, but we can move on.
So next, we're going to talk about mechanisms. So these are basically everything you use in a game to do anything, really. And so first usually follows like a same game process every year, where you first obtain something. So you're obtaining something, you're going to get something. And then your second stage, you're going to move it around. So you're probably going to have to like move it across the field or just bring it somewhere else. And then finally, you're going to have to score that in some way, whether it be stacking it, dumping it somewhere, shooting it into a net, anything like that. And so first, we're going to talk about obtaining elements. And so here are some like historically common ways to obtain elements that we've seen in first. So based on the element type, it's obviously going to vary. So if you're picking up cubes, it's not going to be the same as if you're picking up like stars. But mainly we've seen like grabbers or claws, overhead spinning with like rubber bands, dual side spinning with usually like compliant wheels, which are basically squishy wheels, or we've seen passive things like a forklift. And so like I said, it depends on the element type. In the past, we've seen spheres, cubes, and some unorthodox shapes like those like donuts. And like we've done for the other mechanisms, or other parts of the build, here's some things you want to consider. So when you're building a collection, you want to think about making it 100% reliable, because you'd rather have something work 10 out of 10 times, but it's low scoring, than maybe work 1 out of 10 times that's high scoring. You also want to have minimal lineup, which basically means the amount of time it takes you to like pick it up. So maybe some type of collection, just all you have to do is drive into it, instead of one where you have to like perfectly come at it at the right angle. It's obviously going to take much more time to do that one. You also want it to be fast, because the faster it is, the more time you save. You also want it to be very versatile. So maybe if an element has fallen over, you can still pick it up and it won't matter. And you also want to think about obviously the shape of the thing you're trying to pick up.
So the first type of input intake mechanism we're going to talk about is the gripper. Some of the pros of the gripper are it's versatile for like element shapes. It can pick up things like that relic you see in the bottom picture, or cones is another thing that people used grippers for a lot back in when I was in Vex. However, it usually has a very limited range of motion. It can only really pick up one of those objects at a time. It requires pretty precise lineup a lot of the time. So if you watch some relic recovery videos, you'll see a lot of teams spent a good amount of time lining up their relic grabs. And it can be really time consuming to get that much lineup. And the collection process that's a big part of the collection process for grabbers a lot of the time, is you have to get it exactly lined up to your piece, and then you can grab it. And then the other thing I want to add, I don't think it's a bullet point on there, but grabbers oftentimes will have a bad habit of like dropping game objects when you're moving them around, especially if you're just having the grabber hold on to it. If you transfer it into another like holding section, you usually won't like lose it, but just having a grabber hold it, a lot of times it'll drop that object. Then we have the overhead spinning intake. And its pros are it can have a very fast collection because it's spinning. So you can spin it really fast, and that allows it to just pull elements right in. Sorry, my phone fell. Right into your robot. It also requires minimal lineup, which, as we said before, is one of the considerations. You want to have as little driver input as possible. So for collections like these, all you really have to do is drive your robot into it while you have the collection running. So all the lineup that's required is just getting it on the same line as your robot and hitting forward. And it's really reliable for especially spheres is what it's used a lot for, as you can see in that bottom picture, but it can work for cubes as well if you design it right. However, as you can see on that top left picture, it takes up a lot of space sometimes. So like it's taking up the whole front of their robot, which means they don't get to really put any mechanisms there. And it also requires a lot of material testing. So as you see, none of these pictures have the same material for their overhead intake. And it's going to vary a lot based on what speed you're doing, the placement, everything like that, on what material you're going to be able to use for your collection, the overhead spinning collection at least.
Similar to overhead spinning, there is dual side spinning. This was very common in this past year's game, if there's any second year teams. They are used for unorthodox shapes and cubes, especially if you're using compliance wheels, which will shape around the object that you're intaking. They're very fast and very reliable. Some of the worst things about dual side spinning is that they do require some lineups that you can get it to go straight into the intake, and they're not very versatile. They have some limitations in what you can use them for.
Finally, we have the passive collections, which just mean they're not powered by like a motor or a servo. And so these basically like scoops, forks, cups, which are basically like It has like usually rubber bands in it, and you just drop it on it and it will suck it up, and then you dump it out the other end. And the pros of this are they're very simple to build and they're not complex to maintain. But the cons are usually they require an intense amount of lineup, especially the cups. And they're not very versatile, so usually like they only work for one specific game object.
Once again, I'm not seeing too many questions in the chat. I guess you guys are doing such a good job presenting. But, oh wait, there's one from Ivan. Would you stick with one vendor or we'll try to mix and match? Can you provide some high-level comparison between Tetrix, AnyMark, Rev, and GoBuild?
So generally, if you're trying to do like just parts from a vendor, it's best to try to stick with one vendor because they build everything to fit together. But multiple vendors generally won't, like their build systems don't match up a lot of the time, so it's hard to combine things. One of the exceptions to that is actually Rev because of their extrusion. You can just kind of slap that on anything because the screws can go anywhere. So for our team, on your question about high-level comparison between Tetrix, AnyMark, Rev, and GoBuilda, we our two most common uses are Rev and GoBuilda. We find that GoBuilda tends to be a lot more stable than Tetrix is a lot of the time, and it's just generally easier to work with, as well as they oftentimes have higher quality parts than Tetrix. And Rev is very versatile. You can use it on basically anything because the extrusion will fit on pretty much any hole pattern as long as there's a straight line somewhere in there.
Awesome. And yes, this slideshow will be shared. I believe it will be sent in an email. What mechanism does your team usually use for obtaining objects?
Can I take this one since I'm the intake guy, Jonah?
Okay, sure, go for it.
Okay, so our team, it really varies based on the game element more than anything. This past year, we used a dual side spinning collection with compliant wheels to pull in the like Lego pieces or sky stones, that's what they're called, and it works well. But if we were to try to use that in, say, like Rover Ruckus, it would not work very well because obviously it's specific to the game and specific to the elements more than anything. But our team in general tries to use more of the active and spinning collections if we can, because those are generally, they give you a lot more leeway than grippers and passive ones, as well as they're generally faster because they don't require nearly as much lineup to pull in your game elements.
Cool beans. Okay. I do not think there are any more questions unless another one appears in the next 3 seconds. All right, looks great.
So now we're going to talk about transferring elements. So basically, you're moving something from where you picked it up to where you're going to store it. And so usually this involves like lifts or extensions. And the main ones, or the most common types of these are single bar, chain bar, 4-bar linkage, and linear slides. And one of the unspoken truths about FIRST is they love lifting things. Every game that I've at least done and I've seen in the past, you have to lift something, whether it's been cubes to stack on other cubes or to dump it in the lander in Rover Ruckus. You always have to lift something up. And then again, some things to consider when you're building your lift is you want to make it stable. You don't want it to be able to like wobble a bunch when it's at the top because you might not be able to stack something when it's all wobbly. You're also going to want to think about how high do you need it to be, because you don't want to design a lift that's way too tall or way too small, because obviously if it's too small you can't reach, and if it's too tall then you have a bunch of wasted weight in space. And you want to think about your speed. Maybe you want a slow controlled lift that has a lot of power, or you want a fast lift that just goes as fast as you can. You also want to think about the weight of the end effector. So basically what you have on the end of whatever your lift is. This is especially important for things like just a single bar or a vertical slides, because a single bar, you can often tip your robot if it's too heavy, and same thing with a linear slide. One, you might not be able to actually lift what you're lifting, or it can just topple over your robot, which we've seen a couple of times. Plus, you want to think about a combination of different lifts. So maybe you want to have a lift on top of like vertical slides, which we actually did last year. We put a chain bar on top of vertical slides.
The first type of transfer mechanism that we're going to talk about is the single bar. This is one of the most simple transfer mechanisms that there is. Basically, all it is you attach a bar to a motor. When you run the motor, the bar will move with the motor. It's very simple, but some of the things that aren't so great about it is you have to, you don't have that far of a reach, and the game element will not stay at the same orientation. So if you pick it up parallel to the ground, it will not end parallel to the ground.
And then next is our chain bar, which actually solves one of the big problems with the single bar. So aside from that, the fact that you're adding stabilization to your end to the end result, as you can see here, you start in one orientation and you end in the same orientation, even though you're moving it around a point. It's basically the same thing as a single bar. It's you're using an arm, or you're outputting force, and it rotates it around and it rotates it back. So you don't get any additional extension out of it. You just get what it is. But it does maintain the orientation. However, it can't, again, you have to make sure you're not putting something too heavy on the end, so you're gonna like tip your robot over when it goes like out the back or away from your center of mass, and you don't get much extension out of it.
So the next one that we have is a 4-bar linkage. There are a few different variations of 4-bar linkages. There's a 6-bar and a double reverse 4-bar. Some of the good things about 4-bar linkages is that they keep the orientation of the element very similar to the chain bar. But unlike the chain bar, it's a lot more complex. It also has a smaller maximum height because you can't get it to, you have to keep it from starting inside of your robot, and you can't get it too far out from there. Once again, there's two different types, or two of the different types are the 6-bar and the double reverse 4-bar. Those two are much more complicated than your simpler 4-bar linkage.
Before I start the slide, one thing I also want to add when thinking about your lift is, with the first two types of lifts we talked about, you're going to be grabbing your thing from maybe the front of your robot, but you're going to be depositing it out the back of your robot, instead of these last two, that the one that talked about before, and this one, you're going to pick it up in the front of your robot and you're going to drop it off in the front of your robot. So that's also one thing you're going to want to think about when picking your lift, is that some will change which side of the robot you're on. So for linear slides, these are by far the most common thing you'll see in FTC. I know our team uses them almost every year, and I'm sure most teams do, especially for vertical lifts. And the pros are that you can add more stages to get more height. So really, you could go infinitely high with these. And like I said, they're extremely common. You see them all the time. And the cons are they can be semi-complex depending on the methods, which we'll talk about in a second. And they only go in one direction. So they'll only go vertically or they'll only go horizontally. And another con is, if you want high quality, like really high quality parts, they can be expensive. Like if you want the Sumi slides, they can be very expensive, which it's like a sacrifice of, do you want like nice clean sides, if that costs a lot of money, or do you want ones that may not work as well, but they're a lot cheaper, like Res Kit. And so, like I said, the different methods are string. So if you look at the middle picture with the two yellow balls, the one on the right is what we call cascade stringing, which is that picture. In that picture, there are 3 separate strings. They each go up to a pulley and then down where they're tied. And so that means all the slides extend at the same time instead of one going to the top, then the next one going to the top, and then the next one going to the top, like the snake one, which is the one on the left, which is basically one string that runs through the whole system. And you can also do the snake with chains. And if you want to do belts, you can do snake, but it might be a little harder to pull off. But there are also many different ways that you can do an extension with belts, but they're much more complex to do. And you can also use lead screws, which many vendors sell kits for. And these will give you lots more torque and power. Like in Roboruckus, when robots had a hang, we used a lead screw just because it had so much power behind it. And like I said, it's important to make sure that your lift weighs less than your drive base so that your robot does not tip over. And so now we're going to talk about scoring elements. So how to actually get points. So we're going to talk about some different scoring zones and some tips and tricks. So in the past, we've seen scoring zones that involve launching, dropping stuff, pushing things into it, bouncing on stuff, or lifting either your robot or something up. So really, it can vary every year based on what you're trying to accomplish at the end of your game. And here's some tips and tricks for scoring elements. So the main thing, keep it simple and focus on reliability. You obviously want it to be able to score the most points. And if you do that reliably, it will make you look good for other teams. Maybe because especially if you're a second round pick, teams are looking for reliability over one team that can score a lot of points in like one of their matches. Plus, you want to make it easy for the driver because in a high stress situation, they want it to be easy and as less stressful as they can possibly get it. Plus, research fast games, especially ones that follow a similar suit with what you're trying to do, because you can get so much inspiration from those, as well as looking at other teams, seeing what they're doing, talking with other teams, connecting with other teams that you can do through outreach, and seeing like, oh, maybe I can take some of this inspiration into my own mechanism. So that is all we have for our presentation today. We'll let you guys ask a few questions. I hope you enjoyed it. If you have any questions at all, you can ask them now, or feel free to reach out to us throughout the season, as we would be happy to talk with you and help you.
What he said, we love questions. We thrive off questions.
We really appreciate you guys coming too. We hope you guys are getting a lot out of this, and we're here to help you out through the whole season. Yeah, but if there's no questions, then that's it for this presentation. 2 weeks from now, we will be doing programming presentation. Be super, super fun. Looking forward to it.
Oh, there's a question. I love questions. Okay. What is your biggest piece of advice for designing and building a robot?
So my biggest piece of advice is don't rush through it and keep it simple. Because a lot of times you want to do this big fancy thing that overcomplicates it, and you spend like 2 months doing it, and then you show up to the competition and there is a team that puts something together in 10 minutes that outperforms yours, and it doesn't feel so good. So you really want to make sure that you want to keep it as simple as possible, and you don't want to spend too much time working on it, because you can always spend that time doing driver practice or testing your robot to improve something else or working on your presentation. That's my biggest piece of advice.
Another good thing about keeping it simple is it makes it more likely that your robot will be reliable, which is uber important.
I would say my biggest piece of advice for building a robot is actually to plan ahead, like a lot, especially in the beginning of the design process. You want to make sure you have space for everything, and that like everything works well together. So like for our rover rocket spot, one of our big issues that we ran into was our transfer. So our intake worked well and our deposit worked well, but we didn't plan to get ahead enough. And when we tried to move the game elements from one to the other, we a lot of times we had dropping. So like our elements would fall on the floor and stuff like that. And it was really not a good time if you were driving, because you would do everything right and you would just not be able to score like you wanted to.
All right. Well,
Chris, you just muted yourself.
oh, thank you all for coming out. We'll see you in 2 weeks. It's been great having you.